Sympathetic innervation. Some things here are going to look similar, so hopefully that's helpful. What is this bulgy thing here? This is our medulla oblongata. You know what this is already, the cardio-inhibitory center. So what do you think this one is? This is our cardio-acceleratory center. And of course, again, I have that, it's going to pop up in a moment here. Okay, that is going to innervate our nodes as well. These are sympathetic fibers in this case. So it's going to go down, these fibers are going to go down the spinal cord. As you know, for the sympathetic nervous system are down to the spinal cord, where it's then going to travel out into the periphery. This is our pre-ganglionic neuron. And then we're going to have a post-ganglionic neuron as well. So the ganglia is in that sympathetic chain ganglia, farther away from the effector organ. SA node and AV node are being contacted by these final neurons here. This is going to be ACH, binding to nicotinic receptors. This, right, is going to be norepinephrine primarily, binding to beta receptors within those nodes. Norepinephrine is going to be a positive chronotrope. So is epinephrine. Norepinephrine is the main neurotransmitter released, opposed to from the adrenal medulla. That's going to be our norepinephrine and epinephrine. So how does this work? Similar idea to our parasympathetic nervous system, but this time we need to make the slope steeper. So how are we going to do that? We are going to open channels that are responsible for those funny currents. So one consequence of norepinephrine binding to the beta receptor, activating G proteins, activating CAMP, is of course cardiac muscle stimulation. This can actually open our funny channels. Simple, right? If you open those more, those funny channels are what allow for the funny current, allow primarily sodium, but also calcium to flow down their gradients. That's into the cell. That's what's causing this depolarization. So more rapid depolarization occurs because we're opening up more funny currents than we would at rest. Yeah. So that's norepinephrine. Where does epinephrine come from? Same effects occur with epinephrine. I think I actually have this pop up as a question here. Where would epinephrine come from if we were going to talk about that having the same effects on the heart? Well, that's coming from the adrenal medulla. So it's also very relevant, but it's not coming from the post-ganglionic neuron that comes from the pre-ganglionic neuron that contacts the spinal cord. Instead, it looks something like this. Remember this? So the pre-ganglionic neuron is this one here. We've reviewed this semester already as well. There is no post-ganglionic neuron other than these modified ganglion cells that are part of the adrenal medulla. So instead of having another neuron, these are modified cells that release norepinephrine and epinephrine into the bloodstream. These are going to be hormones because they're traveling in the bloodstream. Released from this neuron is ACH, binding to a nicotinic receptor. Norepinephrine and epinephrine are going to travel throughout the blood vessel, travel to lots of places in the body, but one place is going to be the heart, where they're going to bind to beta receptors. to cause the opening of more funny channels than would have occurred at rest, thereby increasing that steepness of depolarization and causing more rapid heart rate